Hello everyone. This is a continuation of our discussion on molecular structure and molecular geometry. This is the last piece that we'll really focus on. The two main pieces to this set of notes is called hybridization and sigma and pi bonding. There are several extra videos that are posted on our class website that also go into explaining this topic. For today's lesson, you're going to want to have out your notes and a periodic table and probably your homework packet because it has that graphic organizer that you've been filling in to go along with the molecular geometry. All right, so to get started, we've been talking about VSEPR theory. Remember, VSEPR was that valence shell electron pair repulsion theory where we said that molecules are going to spread out as far as possible, or they're going to spread out their bonds as far as possible. So instead of having a bond that was a 90-degree angle, if it was two atoms attached, it's going to spread out so that it's a 180-degree angle. Okay, so they're trying to get those bonded pairs as far away from each other as possible. Okay, it works really great for predicting molecular shapes, this VSEPR theory. But the problem is that there's a lot of different types of bonds that you could look at, and VSEPR theory doesn't really go into looking at why a particular kind of bond forms, or why is it that carbon forms for equivalent bonds and that sort of thing. So we need more models to help us understand why molecules take on certain shapes and why they are formed the way they are formed. Okay, so this first topic we're going to look at this afternoon is orbital hybridization. And it's going to be useful for describing both shape and bonding. So it's going to explain why bonds are formed the way they are, how you get a single bond, how you get a double bond. It's going to help you know the shape of the molecule because it's going to build on our understanding of molecular geometry very nicely. Okay. So first off, you should know from our talk about bonding that bonding has to do with electron pairs. And it has to do with allowing those electron pairs to either transfer completely from one atom to another in ionic bonding, but more importantly in covalent bonding where electrons are being shared. In order to share, orbitals have to overlap. Okay? So covalent bonds occur when electrons are shared really through this orbital overlap. Okay? And those orbital overlaps are when those orbitals take on the same space. So they get close enough to overlap each other and the electrons can transfer from one atom to another. Okay? So hybridization. Think about what a hybrid is. Well, you've probably heard of hybrids before. The most common hybrid that I think of is Miss Sutton's car. Okay, she has a hybrid vehicle, which means it functions as both an electric vehicle and as gasoline powered. So it's hybrid. It allows both to. It has both methods of being powered, and it tries to have a better outcome. You have less gas. It's a lot better gas mileage when you have the hybrid versus just one or the other. Okay, so a hybrid is you're mixing two concepts together and getting something better out in the end. Okay, so what we're going to describe hybridization as for chemistry is we're going to say it's mixing of two or more atomic orbitals. So the p orbital, the s orbital, we're mixing them, and they're orbitals of similar energy, but not the same energy. Okay, in an atom to give new orbitals of equal energy. So if we take an s orbital and a p orbital, we can mix them together and we can get two new orbitals of equal energy. Remember, the s orbitals are lower in energy. Let's see, my little thing stopped connecting. Better? Come to life. Oh dear. Okay, I'll see if I can fix it while we're talking. Okay, so an example, an s orbital is of lower energy than, hold on, it's not going to work if it doesn't. I'll have to do without it then. All right, so an s orbital and a p orbital can mix to form two new identical sp orbitals. And they're no longer of different energies. Remember, the energies are usually lower in energy than p orbitals. Okay? So here's what's going on. In a single bond, if we have methane and we have carbon with 4 hydrogens, okay? Carbon electron configuration is 1s2, 2s2, 2p2. Okay? So 1s2, 2s2, 2p2. So in the orbital diagram, you've got 2 electrons in the s, and then just slightly higher energy, you have the 2 p's, those orbitals, and in this case you've got 1 electron in 2 of those p orbitals. Well, if we were thinking about making a bond with 2 electrons, the s orbitals are already full. The p orbitals are half full, or at least 2 of them are. So we might think, oh, well, maybe it only makes 2 bonds. But in actuality, carbon makes 4 bonds. And the problem is, based on this electron configuration orbital diagram, it just doesn't make sense as to why those carbon atoms can make those 4 bonds. And even if they could make 4 bonds with the s and the p orbitals, wouldn't the s orbitals be different from the p? If we're talking about overlap of orbitals, we've got a sphere and we have dumbbells. They don't have the same shape. They don't have the same volume. They should make different kinds of bonds, right? But they don't. So here's what's going to happen. We're going to take an s orbital, and we're going to take the 3 p's, and we're going to mix them all together. These guys get mixed together and form 4 equivalent new orbitals, and they're going to be renamed sp3. In those sp3 orbitals, these 4 electrons are now going to abide by Hund's rule, and they're going to spread out. And now you have 4 equivalent orbitals, 4 unpaired electrons, and all of these electrons are going to want to make a bond. And funny enough, they're going to be equivalent kinds of bonds. So here's what it kind of looks like behind my writing. You have a carbon atom in the center here. These green lobes are the sp3 hybridized orbitals. They're going to overlap with the s orbital of the hydrogen to form a new bond. And when they do, those orbitals become molecular orbitals, and now this is the shape of methane. And if you recognize methane from earlier homework assignments, you're going to notice that methane should be tetrahedral, and in fact, it is tetrahedral, molecularly as well. All right, so how do we know hybridization occurs? Well, okay, look at that, now it works. Okay. So how do we know it works? Well, we just talked about this really. 1s2, 2s2, 2p2 is our carbon atoms electron configuration. We know it makes 4 bonds. Really, this is what I just talked about. Okay? If we had 2 electrons in the s and 2 electrons in the p, we'd think that those bonds would look different because of the differences in overlap. But they're not. Okay? So this is why we need hybridization as an explanation for bonding. Okay? So carbon does form 4 identical bonds. All right, here's the important piece to this. Okay, so you've got your graphic organizer, and you can start filling in some of the information that's on this chart. So you have, these are the 5 main structures of the on the graphic organizer. We have linear, trigonoplanar, tetrahedral, trigonal, bipyramidal, and octahedral. All of these shapes, there's no non-bonding domains in these. So we're going to start with those. When those molecules have no non-bonding domains, what you're looking at is how many bonding domains they have, and that's how many orbitals you're going to need to hybridize. So with linear is our molecule that looks like this. It has 2 domains. Okay, so it needs 2 hybridized orbitals. Okay, so what it's going to do is it's going to take an s orbital and it's going to take a p orbital and it's going to hybridize them into sp orbitals. Okay, so I'm going to move this over just a little bit. There we go. And that's the hybridization. That's what it's called, sp. So on your graphic organizer, under the hybridization column, for linear, put sp. And that's it. Okay. For trigonal planar, the atom has 3 domains. So what it's going to do is take 3 orbitals and hybridize them. So it's going to take an s, a p, and another p. And the hybrid is going to be very descriptive of this. We're going to call it sp2 because there's 2 p's. So on your chart for trigonal planar, put sp2. Okay. Tetrahedral has 4 domains. So 4 bonding domains. That means it needs 4 orbitals. So we're going to take an s, a p, and a p. And we're going to call it sp3. So any tetrahedral molecule is sp3 hybridized. Okay. Now when you start getting into the bigger molecules, the ones that are trigonal pyramidal and octahedral, trigonal bipyramidal and octahedral, those 2 molecules, you need more orbitals to hybridize. So in addition to having the s and the 3 p's, now we're starting into the d's. Okay, so this the trigonal bipyramidal needs to have sp3 dehybridization, whereas octahedral is sp3 d2. Okay, now what do you do with the molecules that are like ammonia and it's trigonal pyramidal? Well, we're really only looking at how many total domains. So this one has 3 bonding domains, and it has 1 non-bonding. So it has 4 total. When you need 4 total orbitals, we're going to take the s, the p, another p, and another p, and turn it into sp3 hybridization. So the interesting thing is methane, CH4, and ammonia, NH3, are going to have the same hybridization. It's just for methane, all of the bonds are here. This was bad. There we go. For methane, all of the hybridized orbitals are going to be bonded to something. Whereas in ammonia, one of those hybrid orbitals is just going to have a lone pair in it. Okay? So this little lone pair is going to take up one of those hybrid orbitals. Okay? So relate this back to molecular geometry. Anytime there's 2 electron domains, it's sp hybridization. When there's 3 electron domains, it's sp2 hybridization. 4 electron domains is sp3, 5 domains is sp3d, and 6 domains is sp3d2. Okay, and that's all you really need to be able to do, is take the number of domains and turn it into a hybridization. We're not really going to go into the real depth of it all, but these are the things you should be able to do. Okay, so there's a video link that's also posted on our class website. You can get this link there. I want you to pause this video now and go and watch that video. It is going to show you more visually what's going on with the hybridization and show how those orbitals mix and reform new orbitals. Okay, so pause now, go find that link. All right, so maybe you're back from watching that video, hopefully. Let's look at sulfur. Sulfur can make 6 bonds. You remember SF6? So sulfur had 6 valence, fluorine has 7 times 6 is 42. Sulfur hexafluoride looks like this. Really cool molecule. Lots of electrons. Lots of electrons. Well, why is it that sulfur hexafluoride can make all those 6 bonds? First off, what type of hybridization is it? How many domains are here? I see a total of 6 bonding domains. Okay, no non-bonding, so 6 total. That means I need an S, 3 of the P's, and 2 of the D's. So sp3d2. That is my hybridization for sulfur hexafluoride. Well, how can it have d orbitals participating in bonding? Well, sulfur is the electron configuration. If we look at our periodic table really quick, sulfur is here in the 3rd period. It is 1s2, 2s2, 2p6, 3s2, 3p6. Well, what else is in the 3rd energy level? In addition to having the 3s2 and 3p6, it also has the 3d orbitals. They're just empty. Okay? And so what it's going to do is it's going to enlist some of those not currently being used d orbitals and hybridize them. Okay? So the d orbitals are empty and they're going to then be pulled in. So we're recruiting them for duty. Okay? So we're going to take the 1s, the 3p, and the 2d in order to mix them and form 6 new identical sp3d2 orbitals. Okay? And this molecule is octahedral. Those hybridized orbitals are going to form the octahedron. All right, so let's do a quick quiz here. I would recommend pausing the video and trying to solve these on your own, and I will go through them as well. Okay? So pause your video and try to answer this quick quiz. All right, so now I'm going to go through it. PCl3, phosphorus trichloride. You do the Lewis diagram. Phosphorus is 5, chlorine is 7 times 3 is 21, so 26 electrons total. We're going to put phosphorus in the middle. We're going to put chlorines all around it. And those 3 chlorines use up 6 electrons, so I've got 20 left. 6 for each chlorine, so I've just used 18. I have 2 left. Where do they go? Right there on the phosphorus. So if I'm looking for the shape of this molecule, I'm going to see that there are 3 bonding domains, 1 non-bonding, total of 4. If there's 4 total domains with 1 of those non-bonding, what shape is it? And looking at your chart, you should have said trigonal pyramidal. Okay? If it's trigonal pyramidal, the bond angle is 107 degrees. Now the hybridization. With hybridization, I emphasized using the total number of orbitals, 4. Since there are 4 total orbitals, we need the s and then 3 of the p's. So that is sp3 hybrid. Okay? All right, so it's sp3 hybrid, and that's really all you need to be able to say on one of my tests. Is I'll ask what is the hybridization? You just look at the number of domains. Okay, so if you can do the Lewis diagram, you can pretty much get hybridization A-OK. The last question is the molecule polar or nonpolar? Well, in the last set of notes, you learned that trigonal pyramidal is an asymmetric kind of molecule, and so it is polar. Okay, that's it. For the next one, CO3 with a 2- charge. Carbon is 4 electrons, oxygen is 6, times 3 is 18, 18 plus 4 is 22, plus 2 is 24 electrons. So I'm going to put carbon in the middle, oxygen's all around it, I used 6, I have 18 left. Put my 18 in, no more left. Is it all okay? Carbon needs an octet. So what do? Well, I take away one of my pair of electrons, and then I reform a bond here. Well, since I could have put that electron or that bond anywhere, here or here, that means I have resonance. I'm going to save myself some time and not draw them all out. Oh yeah, and I needed brackets. Okay. All right, well, what shape is this? I see 3 total domains, all bonding. So this means trigonal planar. Okay. Well then, if I'm looking for bond angle, this bond angle is, this molecule is totally flat, so the bond angle would be a circle divided into 3 sections, so that's 120 degrees. Since there's 3 total domains, that means I need an s and 2 p orbitals. That makes sp2 hybridization. Okay, so now I've done the shape, I've done the angle, and I've got the hybridization here. Is this molecule polar? Well, looking at the shape, which is trigonal planar, the shape alone says asymmetric. If I look at all the outward elements, this guy, and this guy, these are all the same, so it's symmetric atoms, and it is symmetric as a shape. Hopefully I just said that. Okay. All right. Proceeding onward. So sometimes we can have molecules that have multiple bonds, and I want to show how hybridization leads to these multiple bonds. This part is a little bit more abstract, so you have to really use your memory or your imagination here. Okay, so a bond is formed from the overlap of orbitals, right? And orbitals can overlap in different ways. You can have head-on overlap, so if you've got 2 sigma orbitals overlapping, or if you have 2 p orbitals, or sorry, these are 2 s orbitals, and these are 2 p orbitals overlapping. Okay, this is considered head-on, and this is called a sigma bond. Okay, you can also have side-on overlap. That would be as if you had 2 p orbitals that came in like this and overlapped. This is called a pi orbital. Okay. How does this happen? Well, when we're doing hybridization, sometimes there's orbitals that don't participate in the hybridization. So if you're using sp2 hybrids, that means you've used an s and 2 of the p's, but the third p is still there. So it doesn't participate in hybridization, and it just hangs out otherwise. Okay, it doesn't have any electrons in it. So from the side view, it looks like this, and from the top view, it looks like this. Okay. So for ethylene, ethylene is a molecule that has a double bond. What it ends up doing is the carbon will have the sigma overlap, and then it'll have its other 2 hybrid, and these are from the hybrid orbitals. Okay, it's going to then bond with the hydrogens like this. But then it's got these p orbitals that are hanging out, and the p orbitals are sticking out so that they can have some overlap. Okay, so in ethylene, it has a sigma bond, and it also has a pi bond. So a double bond is a sigma and a pi because of the overlap of the orbitals. With triple bonds, it's because you have sp hybridization, and so you've got two p orbitals hanging out. So the carbon will have, these are the hybrid orbitals for sp. So there's a sigma, and then it's going to overlap with an H and another H. So those are these are other sigma bonds. But then you've got these p orbitals that can overlap. There's a pi bond. And another color. We'll go blue. Okay. But then perpendicular to that, there's another p orbital. So there's another pi bond. So a triple bond is a sigma and a pi and another pi. I love pi. Unfortunately, Pi Day was a week ago. Okay. All right, so really what do I need to know about this? Because this is really complicated, Mrs. Bilkey. I don't even know what you're talking about right now, right? Sigma bonds are the head-on overlap, and it's when you have an S and an S overlap, or you have an S and a P, or a P and a P overlap. You really don't need to memorize this. You just need to know it's head-on overlap, okay? And here's kind of a little visual to show you that head-on overlap. Okay. And it kind of rearranges itself. A p orbital can also do that head-on overlap. When it does, they squish together and reform, and the new molecular orbital looks like that. Okay? Not a big deal. Okay, pi bonds are when you have electron density above and below because of this, those crazy p orbitals that weren't part in hybridization. Okay? So the overlap is less. There's not as much overlap. Pi bonds typically are weaker bonds than sigma bonds. Kind of an important piece. So maybe write down that part, that pi bonds are in fact weaker than those sigma bonds. Okay. Here's a visual to show you what's going on with the orbital overlapping. And that's what it does. When it does the bonding, it reforms and it shows like this, with this above and below business. Okay, so that is called a molecular orbital after it's bonded. So here's the big takeaway. Anytime you have a single bond, it's a sigma. If you have a double bond, it's a sigma and one pi. See? Right here. A sigma and pi, and that's it. If it is a triple bond, it's a sigma and two pi bonds. That is the main takeaway from this pi and sigma bonding business. So when I give you a molecule, see, that's it. If I gave you a molecule like this, so here's a molecule. What I could do is I could ask, what is the hybrid? And I could also ask, how many sigma bonds and pi bonds are in this molecule? Ooh, let me make this, there we go. Okay, so I could be looking at, on this molecule, if I'm going to count up, first if I'm going to do hybridization, if I'm looking at just the carbon atom, I see that there's 1, 2, 3 domains around that carbon atom. So then I'm going to say I'm going to need an S, a P, and a P. So it has sp2 hybridization for the carbon. If I look at the oxygen, there are 2 bonding, 2 non-bonding domains, and so that's 4 total domains. So this is actually sp3 hybridized. So you can have pieces of the molecule that have different hybridizations than other pieces, and that's fine. Okay. If I look at how many sigma bonds there are, I just need to count how many bonds are there total. So I see 1 right here, 1 right here, 1 right here, and 1 right here. So that is 4 sigma bonds And then I need to, if I'm looking at pi bonds, that means I need to look for any double or triple bonds. I've got one double bond. And if you recall, a double bond is a sigma and a pi. That means there must be only one pi bond. That's it. Okay. Those are the kinds of questions I would want to ask you. They are not very complicated. They're not in depth in the background, in the content. I just want you to be able to apply it. Okay. So on your homework, it's the molecular geometry practice. There are questions that ask you for the hybridization of molecules, and there even is a question asking you about sigma and pi. You can expect those level of questions on a test. Okay? I've also posted more helpful websites again. Please use them. Make sure you are using all the resources you can. And send me questions if you have them, and I can try and address them as quick as possible. Okay? So hang in there, and I will see you again soon.